So here's an example of something I might give you. So one might be something like this. X equals y equals. So I wanted to do something like this. 2, I wanted to do cotan t, let's say plus 1. And I wanted to do something like this. 3 cosecant t about minus 2. And then I'm going to ask you, now, on some of them I might ask you to graph. On something like this, I might not. But at any rate, I'm going to give you this, and I'm going to say, find an equation in x and y that has the same points as this. And of course, I would give you some kind of t is in 0 to pi or something like that, right? And if I may or may not tell you to graph it. And let's just say, for the sake of simplicity, I'm not asking you to graph this one. But I'm going to tell you to find an equation in x and y that has the same graph. And I'm going to tell you to identify the object. And so, if you were faced with something like that, what would you do first?
Solve for t.
Okay.
Well, that probably wouldn't work.
Probably wouldn't work. And that's the thing, right? You have trig functions in here. So you're already thinking, well, like for instance with the x, if I get everything except for the t all by itself, I'll have a cotan, and I could do an arc cotan maybe?
What thing?
Yeah, well, no, what I would do is I would rewrite it as 1 over tan, and then you have stuff, and then I would say, well then tan is 1 over stuff. If you absolutely had to solve for t, then you'd take arctan, and at this point you go, it's like 1 over, and you have like an x squared plus y, blah, 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 and you're like, I have no idea what that is. No clue whatsoever. So that's not going to help you with this because you're supposed to identify the object, right? And tell me what object this is. So in this case, you probably don't want to try to get that t all by itself, but what could you do?
Get the cotangent by itself.
Let's start by getting the cotan by itself. And let's see. So what do I need to write?
2 cotangent equals...
Okay, 2 cotan equals?
X minus 1.
Alright, so x minus 1. Now,
1/2 x minus 1/2.
yeah, we can do it that way, or we can do it like this. Okay, so now we got that. Now what?
Wait.
That equation, I'm going to say, is about as good as it's going to get.
Yeah, so the other one.
So let's work on the other one. Yeah, and so what do you want to do with that?
Get cosecant by itself.
Get the cosecant by itself, and so
It'll be y plus 2 over 3.
plus 2 over 3 is equal to cosecant t.
And then we probably have
Can we
something that
relate
relates.
Now, how do we relate cosecant? So here, I'm boxing. These are not the final answers. It's going to get ugly, and so I want to be able to easily come back to where we were. So yeah, we want to. How do we relate cotan and cosecant?
Well, we can just, I don't remember it, but sine squared plus.
There you go. And neither do I. I never remember it either, but I know that sine squared plus, and notice I'm not even writing the t, right? But cosine squared is equal to 1. Now, how do I get either a cotangent or a cosecant?
Divide everything by cosine. Oh no, by
I
sine.
divide everybody by not just sine.
Wait,
Sine squared. Right. So if I go sine squared, now this turns
you
into
get 1 plus
1
cotan
plus cotan
equals
squared.
CSC.
Goes
Cosecant. Cosecant squared.
Now we can
CSC. Get out of here. Okay, right? And so that's the idea. Now we can see, okay, how could I relate these guys together? And what am I going to do?
square both sides
Well,
of the, because we have to.
yeah.
Oh, you mean over here? I thought you meant over here. I'm like, no, it's going to make your life so much
Well,
worse.
if we made it 1.
And so, right, and that's what I was kind of getting at, is I want to get this guy to have the 1 by itself first. first. 1 equals cosecant squared minus cotangent squared. Now I have an idea. I have a goal. Because if I could get, I noticed that I could square this thing, or square that thing, and then subtract off that thing squared, then I'll have something. And so that's what I'm going to do, right? So let's just square both sides, right? Like you said. And I'm going to go ahead and do it this way. X minus 1 quantity squared over, I'm just going to write it as 2 squared, is cotangent squared of t. This one, and the reason I'm doing it this way, I mean, I could, if I wanted to, I could just do this. And that's true. It's just that from last year, if you remember, right, all of these types of things, right, we usually wrote them like this because it helped us identify. And if you were going to go on and graph this, having it like this would make your life a lot easier. But it's not necessary, right? It's just one of those things. And there's another reason why, Noah, when you said, over here you said, oh, 1/2 x minus 1/2, it's like, yeah, you could do it that way. But then you'd have 1/2 x minus 1/2, and you'd go and square it. And it might be hard to see from there when you go to put all of this together in the end. If you have it looking like this, it might not be so easy to see what the thing is in the end. But it's correct. It's absolutely correct to do it that way. It's just, it's going to look a little different. So now, okay, now what do I want to do? Since I know that cosecant minus cotangent is equal to 1,
So
then
minus the first one.
there you go, right? So I'm going to take this one, which is y plus 2 quantity squared over 3 squared minus x minus 1 over 2 squared. That's the same thing as cosecant squared t minus cotangent squared t, which is equal to 1. And therefore, now here is my equation in x and y. Oops. Oops. There's my equation in x and y that has the same points as this thing. Maybe not all of them, it depends, but like, yeah, that's the idea. Now, what is this thing?
Hyperbola.
Hyperbola. Okay, so yes, hyperbola. That is a hyperbola. Now, similarly, if I said, prove that this is a hyperbola, I would expect you to do something like this and go, that's a hyperbola. We know that from last year. We don't need to go and prove that this is a hyperbola. But to show that this is a hyperbola, we would need to go through these steps and end up here, back to something that we know about and say, well, we know that equations like that are hyperbolas, therefore, this thing back here is a hyperbola. Now, since we're reviewing for something, let's go ahead and graph it. Okay, does anybody remember how to graph these things?
We'll first figure out which way it opens.
Yeah, let's figure out first which way it's opening. Okay, so I know that, and I was going to tell you, I'm not going to tell you to graph a hyperbola, but let's do it anyway. First thing I would do is pretend that it hasn't been shifted. So I'm going to graph the hyperbola y squared over 3 squared minus x squared over 2 squared equals 1. And then I'm going to take whatever it is and shift it. So we know that in this case the center is right here. And so it's either going to open like this or it's going to open like this. And then I'll shift it whichever way afterwards. So, okay, which way does it open? Up and down or left and right?
Up and down.
I think up and down, and let's just see.
Because
If it does open up and down, and this is how I would graph it, I would guess one and say, I think it's this way. Now, does that make sense? Well, what happens when x is equal to 0? When x is equal to 0, that part goes away, and you're just left with a y squared over 3 squared is equal to 1, so that y squared is equal to 3 squared, so that y is equal to plus or minus 3, and so you have a 3 here, a minus 3 here, and you're good to go. That looks great. But if you did it the other way, let's say you guessed wrong, and you said, ooh, I think it's like this. Yeah, because it's the minus x, and so it's going to do this. You're wrong. But you'd say, okay, well then where does it cross an axis? I guess it crosses the x-axis whenever y is equal to 0. So I plug in a y equals to 0, and I get negative x squared over 2 equals 1. So that I get x squared equals negative 2 squared. You take a square root and you find, oh no, that doesn't work. So it can't be this one. And so now we're back to here. Then from there you're just shifting, right? And I might have you graph a hyperbola. I might do that. That would be nice. But what I won't do is tell you to find the asymptotes, right? I'm not worried about asymptotes in this class right now. But here, I'm going to shift it. And which way am I going to shift it?
To right.
How many units?
1.
Right 1.
Down.
Right
Down
1, down 2. And so we would be here at 1. This would then be at 1. This would be, it was at minus 3. We went down an additional 2, so I guess minus 5. And it does this thing here.
Do we have to find the intercept?
I would no, not on this quiz, no. But you should be able to do that. Now, but here's the problem, right? That's not what I told you to do. Right? This is that. And that is not that. Because remember how they phrased it in the homework was like that share, like the set of points that share the same, that they share a set of points. It's not necessarily this guy right here, right? So what we would need to do then, what would we need to do? How do we figure out, because we're trying to find the orientation. Is it this bottom one? Does he go this way? Is it the bottom one that goes this way? Is it the top one that goes this way? Or is it the top one that goes this way?
Don't need to graph it on.
Plug in this.
I would graph x and t first. That's what I would do. I would say, okay, and there's all my work. I'm going to say, let's just see what x does as t. So 2 cotan, I know cotan basically does this thing, right? And so here's pi. Here's pi over 2. And the 2 would stretch it, the 1 would lift it up, but he's not going to be moving left or right, right?
Yeah.
Right? So this is just cotan. And so if I do 2 cotan, it just stretched it. Plus 1 lifted that up some, but who cares, right? That's not the idea, right? It's not gonna change that much. And so I could see then as t goes from 0 up to pi, because that's what I said here, then x goes from where to where?
Positive infinity to negative.
Positive infinity towards negative infinity. So I'm saying as t goes on, right? And now I'm imagining we're just talking about a point moving on the x-axis. As t starts from 0 up to pi, then I'm imagining that what's happening with x is that the x is just moving in this direction. So in both cases, it's either doing this or it's coming from here and doing this. Now we just need to figure out, is it the top branch or the bottom branch? So let's look at y. So we know what x is doing in that time. Now let's find out what y is doing. So cosecant is 1 over what?
Sine.
Okay, so I'm trying to graph y equals, I'm going to start with cosecant, just plain old cosecant t, which you said is 1 over sine, so I'm going to think, okay, if sine does this, and I don't need to worry about anywhere else because I only care about what's happening between 0 and pi.
Isn't that 0 and 2 pi?
That is 0 to 2 pi, yeah. And as I was writing that, I was thinking, I don't need this. I only need this first bit right here, because that's pi right there. And there's pi over 2. And so cosecant does this. So he drops in from infinity, comes down to 1, and then shoots back up to positive infinity. And so now I'm going to multiply that by 3. And so when I get my 3 cosecant, now I've just stretched it. That's all that's happened, is I've gone up to 3 and down to negative 3. Right? Everybody got that? Now when I subtract 2, he's still positive, right? I bring all of that down by 2. I'll do it just to be clear of what I'm doing. I'm just bringing from 3, subtract off 2, it comes down to 1 now. And so it's the same picture. It just does that. And now we have, there was my sign or whatever. And I guess that's it. That's all we need to know. So as t goes from 0 up to pi, y does what?
Goes down from infinity, stops at 1, and
There
then
we
goes
go.
back
So
up to.
from infinity down to 1, and then is it back up to positive infinity. So what I should expect in the y direction is that here's y. He's coming down from positive infinity down to 1 where he stops, and then moves his way back up, right? And so putting those things together, it would look something like this guy's coming in from infinity, this guy's coming down from infinity, he comes down, pops here, and comes back up. It's got to be the top branch, and so this would be the orientation. Just like that. Extra credit. At what time does it hit this point? Time t, of course. For what value of t does he hit right there?
Pi over 2.
I'm guessing because we haven't shifted this guy over left or right, and the only time the y value comes down to 1 is right here. At pi. It should be pi over 2. It should be halfway between 0 and pi. Right? Because sine does that. Sine has a max here at pi over 2. And so yeah, when t equals pi over 2, he's made it right there to the middle. That kind of makes sense because it's also halfway between the interval, and it takes, you know, I mean, yeah, that's not necessarily the case. You might have some crazy stuff going on in here that might shift or whatever, right? Like if it were instead x equals 2 cotan 3t minus pi over 6, I wouldn't do that to you. But like, I'm just saying, oh, it's not always going to be halfway in between. Like, this might mess things up a lot, you know. But yeah, anyway. Okay, any questions on that?
Well, we got our little card thing with the formula. Do we not need that?
You don't need that. You shouldn't need that. Yeah, I'm not going to give you any kind of crazy, like, because I think in the homework there were a few where it was like, you needed to know some stuff about, like, because you had like a cosine,
Like 2 theta.
2 theta, right?
Yeah.
Although, I mean, it's really, this is one of those ones that you really, 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 really want to remember is that this is true. From there, you could get 2 cosine squared theta minus 1, which is the same as 1 minus 2 sine squared theta. That right there is one of those things you want to know forever. And I'll try to avoid that. Yeah. And all those other crazy stuff, you won't need to worry about that. So that should be good. All right. Questions?
How many problems is the quiz?
Don't know. It's probably gonna, at least 4. At least 4. Because there's going to be one like that. There's going to be one like another parametric equation that probably doesn't involve trig, right? So something like this. Let's just say reals. There we go. Okay. Well, what's this?
Get t by itself.
We can rewrite it.
Yeah.
Oh wait.
Something's.
I mean, you could get t by itself.
We have to use natural log.
You could.
Or
You
you
could-
could write it as.
You could do this. You could say natural log of x. Natural log of that is just 2t. Natural log of y. Natural log of that is just minus 4t. Get the t's by themselves. This is log x. Peter, calm down. Divide by negative 4 equals t. Set those equal to each other, and you have natural log of x over 2 is equal to negative natural log of y over 4. I'm going to bring the 4 up. Cancels gives me a 2 log x is equal to, I'll bring the negative over here too, why not? Log y.
We have to put the E in.
It won't work
No,
unless
I
you
have to
get
put
that
that-
up
oh, wait,
in
no.
there. You got to do this first. X to the negative 2 is equal to natural log y. Now we do our e's. And you get e log is y. E log is x to the negative 2, which is 1 over x squared, so that y equals 1 over x squared. And you can do it that way. That would be fine. Another way, another way would be to say, wait a second.
That's bad.
This is almost the same thing. Like the only difference here is that, and this is what I noticed right away is like you have a e. It's basically e to the t squared, but whatever, e to the 2t. And why don't I hate negative exponents? Why don't I just write it like this?
And then that's e to the t.
That's just e to the
To the
2t to the 2,
yeah.
right? Like this is the same thing
means it's-
as e to the 2t, but then squared.
Just substitute in the
Which is just, yeah, just substitute it. And your life is much easier that way. Much easier.
And do we graph it?
And yeah, and then graph it. Can you graph that one?
We could try.
Have we graphed
It's
that
like
one?
it's like
plug
a
in
hyperbola, but then just
You
flips
could
up.
plug in points. Oh my goodness.
It's like the side, the turned hyperbola, but then you like flip it up.
There you go. That's a great way of thinking about it. Like, and that's how, if I didn't know what this thing looked like, if it weren't already beat into my head what this thing looks like, I would say, well, you know what? I know what y equals 1 over x looks like. And then if I just take this and square it, let's just see. So y is 1 over x would look something like this. That's our old friend there, right? He goes through here at 1, 1. And then negative 1, negative 1. And then if I just take it and square everybody, I guess nothing really happens there. The things bigger than 1 get stretched up. The things down here get stretched down, but qualitatively it's going to look the same. The only thing that's going to happen is when I square the values, really, is it's just going to take all the negative values and make them positive. And so this would be the graph of y equals 1 over x squared. That's how I'd do it. And yeah, you're like, well, but you didn't stretch that up or down. I was like, yeah, I didn't do a good job graphing it in the first place, did I? So I mean, like, it's like it looks the same whether or not you actually made this a little bit bigger up here and made this come down a little bit more here. Whatever, like it's fine, right? Everybody understands why it stretches down, right?
Because 1 over.
At some point, right, you're here at like the regular 1 over x would just be. You plug in a 2, you get out a 1 over 2. But now you're just taking it and squaring it, and when it's less than 1, you square something that's less than 1, and it gets smaller, right? So this drops down from 1/2 down to 1/4. Whereas over here, plug in a half, you get out a 2. And then when you take that and square that, it jumps up to 4, right? So the 1 stays put. Because 1 over 1 is the same thing as 1 over 1 squared. But yeah, so, but then what branch? Or is it both branches? What's going on?
Oh.
Let's figure this out. So we have our candidate, or we know what this thing is. This is the same thing as y equals 1 over x squared, which looks like this.
Figure out which way it goes.
But now we need to figure out, okay, is it both branches? Is it one branch? Is it going this way? Is it coming down this way? Is it going up this way? Is it coming that way? So what are we going to do?
Graph the other things.
Just graph the things. And so x of t,
It's
Goes
just.
through 1.
it goes through 1 and that's an exponential. So as t ranges over the real, so as t goes from negative infinity up to infinity, x goes from what to what?
Negative, no, 0 to...
Yeah.
0 to infinity. So I'm seeing x is going from here, not quite there, but all the way up. So I pretty much know what's happening. And if you're really not certain what this is gonna look like, you could stop and say, well, let's just do it with the y too. Just make sure that everything works with the y. So that's x. Here we're gonna graph y versus t. And what does that look like?
It's coming down.
Coming down. Yeah. What you could think about it is you flip it in that direction, right? Or you could also, see that as, well, it's 1 over this, 1 over e to the 4t. So it used to be that when you plug in really, really small numbers, this thing would be really small, but now you're dividing by it, so it makes it really big, right? And so on and so forth. But nonetheless, as t goes from negative infinity up to infinity, then y goes from infinity to what?
To 0.
0. And so y is coming from infinity and approaching 0, and indeed that's what this looks like. It should be this branch right there. It should be that one. This guy is not part of the graph. Alright, so we got those?
Yeah.
There's a smart way of doing it, but of course it's a quiz, right? So it's like you might just biff it, right? And if you do, don't worry, you'll get there, right? Just like we did with logs and all that.
That's what that is.
Everything worked, but
That was a surprising noise.
you can make it hard on yourself. And and this is the thing, and this is why I wanted to do 2 problems like this, was that we didn't need to get t by itself. In fact, getting t by itself turned out to be more work than we needed. But if you do, it's okay. You'll get there. It's just
But the first one you might not get there.
Yeah, the first. Good luck, Peter. Please, not right now, buddy.
I did a good job.
Yeah, but let's try to keep it down, please. Thank you.
No.
So that's parametric equations. I might give you something and say prove that that's a hyperbola. I already told you. I already showed you.
Yeah.
Well, that's a thing. It's a possibility. Okay. Yeah. So, any other questions about what are these things just called? Parametric equations.
Because you're that toys.
Parametric equations.
Variety of toys. Later in
Okay, then polar coordinates. You probably have 2 parametric equations. Everything else will probably be polar coordinates. And if you remember, I love this because you have to know everything from trig to be able to do some of these. Right?
Yeah.
That's just
And everything from last year.
And everything from last year. It all comes together right here. So, any specific questions about polar coordinates?
We have to graph like the big flower things on the quiz.
You might have a flower. But I'll guarantee you that it won't be more than something like. Let's do it. Let's do one. Let's do a 2 sine 2 theta
Okay, that's not that.
plus.
More than like 4.
Yeah, if it's more than
Yeah, right. Those are bad. I can guarantee you it won't be more than a 2 theta.
Okay.
And let's do plus. Let's just make it rough.
Wait, if it's
Let's
like
make
5 theta, it's still just 5. It wouldn't be 10, would it?
If it were 5
If
theta.
it's an odd number, it's.
Oh, gee. No, it's still double the number of things.
But there was one that was sine of 3 theta, and when we did it, it was only 3. It only came out to be.
That can happen. It depends. Okay, so that's another thing. Is like if it does something like this, then you end up going back over parts that you've already gone over, right? And that's the thing. So like you might trace one out like this, and then it comes down like this, and then it comes out like this, and you're still only at pi. But then as you go on, you end up tracing the same ones, and that's cool. But and that'll work that way. Actually, I think that's when it's perfectly split. If it's perfectly split, like right in the middle, so there's no shift up or down, then you might end up with something like that. Yeah. But in the other way, like, yeah. So let's do this. This one should be rough. We might as well do something rough. So, okay, I'm gonna give you this and say graph in polar coordinates.
Not funny. Not funny. No, I'm just hate something.
All right.
So first, graph.
First step. Yes.
Graph it in X and Y.
Or graph it in Cartesian coordinates, right? So that's what I'm going to do. Here's theta. Here's r. And so sine. So I'm thinking, okay, sine normally does this. Okay. And double it, and so it goes up to 2, down to -2, but then I'm going to shift it up by 1. And so the new thing is gonna be like right there. So it's gonna start, and I'm gonna go ahead and do my 1 right here because that's gonna make my life a little easier if I have that to orient me. Now we'll do 1 full period like that. You can see I did not draw this very well, but it will work for our purposes, okay? And knowing that it's 2 theta, I might as well go ahead and do like that. Now, each of these points are easy to get, so let's go ahead and get them. So normally this would be 2 pi, but since we're doubling it, this is what?
Pi over 2.
Oh, no. It's
Pi over 2.
Just pi.
Oh, just pi.
Yeah, okay. This is 2 pi. That's how we should have started. But like, you know what I'm saying, right? 2 theta is to 2 pi as theta is to pi. So this thing does 1 full period after pi radians. And so now, okay, half, that will be pi over 2, meaning that this one is pi over 4. So 1 pi over 4, 2 pi over 4, this would be 3 pi over 4. These points are going to be needed. We'll get them soon.
Wait, the 0.
The zeros will be very necessary in order to do the right graph. And so, okay, now we're counting by pi's over 4. We have 4 pi over 4, meaning that this is 5 pi over 4.
And then 3 pi over 2.
There we go. That's what we could call it. 3 pi over 2. These we don't know. Those are the zeros, which we'll come back and get. This one is
7 pi.
7 pi, because yeah, 5 pi over 4, 6 pi over 4, 7 pi over 4. Then we have that last 0, and then our last known point. Okay, one more thing. What are the heights here? What is the big height, the top height? 3, yes. And then down here it's
-1.
-1. Okay, now let's find the zeros. We're expecting 4 of them here. And so I'm going to say, okay, when r is equal to 0, then this thing, we're going to bring this over, -1/2, cut to the chase here, sine 2 pi. Okay, so how do you want to do this?
Arc sine of -1/2 over 2.
Okay.
Or, well, no, we should
Just
just
pretend the 2 thetas
yeah,
are
just
theta.
draw the triangle.
It'd be much easier if you draw a triangle, right? So what I'm doing here is I'm pretending that we have like a sine x, where x is 2 theta, right? And if that's the case, then the 1/2, which triangle am I drawing?
1, 2, root 3.
1, 2, root 3. And so sine, how do I get a sine 1/2? Which one of these?
Pi over 6.
Pi over 6. There we go. So
But
I know that pi over 6, sine of pi over 6 gives me a 1/2. And so my possibilities will be pi over 6, 5 pi over 6, 7 pi or 5 6
Seven.
7 pi over 6 or 11 pi over 6.
It's gonna be 5 and 7.
But now, hold up.
Is-
And then and then those are the
Pi over
negatives. So when sine is negative,
Oh,
which ones
the
are these?
7 and the 11.
There we go. 7 pi over 6.
Right.
And then 11 pi over 6. We'll do it. But that's for x, right? So in other words, x is equal to 7 pi over 6, where x is equal to 11 pi over 6. That'll do it. But x...
Oh, we divided by 2.
Now we divide it by 2.
Because it's 2 theta.
Because it's 2 theta. X is the same thing as 2 theta, right? 2 theta. But this is also, this is what's so hard about this. This is 2 theta equals 11 pi over 6. But not just 7 pi over 6 and 11 pi over 6, plus all 2 pi multiples of these guys.
Yeah.
So this is one way you could do it. Then you divide through by your 2. And in the top one gives you theta equals 11 pi over 12 plus pi again. And then the bottom one gives you 7 pi over 12 plus pi again. That makes sense, right? Yeah, anyway, so that's one way you could do it. Another way you could do it is think, well, hold on. Like, back when this was just regular old sine x, right? If this were sine x and not sine 2 theta, then this would have been, these would have been those two bits that you found. This would have been 7 pi over 6. That one would have been 11 pi over 6, right?
Yeah.
Right? If you had just drawn sine x, if this were an x instead of a 2 theta at the very beginning, you'd get down to this point. But then what did we do here? How did we find all these? We just divided everybody by 2, right? And so you get those 2 points and you divide them by 2 and you would end up with the 12 and the 12, which are the 2 that we found. Yeah. But we also would have ended up with the other ones, right? Because this keeps going, right? Like this. And then it's just a question of, well, what were these other 2 right
Just
there?
add pi.
And you would have just added, yeah. Or if you were saying, well, if this were sine x, this would be pi over 6. That would be 11 pi over 6. And so then you'd add 12 pi over 6 to that, right? Or 2 pi. So 12 plus 7 is what?
19.
19 pi over 6. And 11 plus 12
24.
23.
Yeah.
23 pi over 6. Then you take it and say, wait a second, it's actually 2 theta, so everybody got squashed down. And so now you have a 12, and a 12, and a 12, and a 12. Which is what you would also get right here, because you know it's the next 2 that show up. And so you add 12 pi over 12 to that, and you get that. Add 12 pi over 12 to that, and you get that. And so you got them, right? So now, okay, so let's get these up here. We have 7 pi over 12, 11 pi over 12, 19 pi over 12, 23 pi over 12. So you can see this one's wicked hard. Like already, like you've pulled out everything you've learned in trig up until this point. I love these problems. Love this. Now you have to graph it in polar coordinates. So, okay, we need it. Let's find every single one of these. Okay, we're gonna identify all of them here.
It's gonna be like looping around.
Oh, it's gonna be crazy. It's gonna be so ugly. It's gonna be terrible. So, okay, we have pi's over 4. Okay, we have pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Blah, blah, blah. And so I'm gonna go ahead and just get those out of the way. There's pi over 4.
Very scary and sad. Will they be able to save her?
That's 5 pi over 4, thank you. And this one right here.
So much better.
And this is 3 pi over 4, making this 7 pi over 4. Now, okay. The other ones, I think we have 0, which is good. Pi over 2 is one of them, so that's good. Pi is one of them, so that's good.
3 pi over
3 pi over 2 is one of them, so that's good. Now we have these 4 ugly ones, but the thing to think about here is this. Like, that's half of a pi over 6.
Yeah.
So it's like
So,
in between.
Pi over 6, yeah, if you imagine what pi over 6 does, it's kind of like this. So half of that would be that. We just need to figure out where they are. And what's nice about this is, check this out. There's pi over 2. So there's one between pi over 2 and 3 pi over 4. There's pi over 2. There's 3 pi over 4. And it would be like 6 would be here, but now it's smaller, so it should be higher up. Right? It should be closer to the pi over 2 than to the 3 pi over 4. If you do it the wrong way, I don't care. As long as you're consistent with this. I mean, really, you could make it look like a pi over 6. I'm not going to care. As long as it is indeed between these two, like it says right there. If it's between those two, we're good. We're golden. This is 7 pi over 12. Yeah. Now, 11 pi over 12 is between what and what?
Pi and 3 pi over 4.
There you go. So it should be between these. And 11 pi over 12 is just 1 pi over 12 away from pi. So there's no question of which way to go. It should be the shallower one. It should be shallow. And so there's 11 pi over 12. Now, the other ones. We have... So now one thing to notice is 23 pi over 12. It's almost 24 pi over 12, which would be 2 pi, which would be back at 0. So I could see, aha, that is the other part of this guy right here.
So then the other one
Isn't 19
probably
the other part of 7?
I believe so. And let's just check here, because 3 halves and 7 quarters. 3 halves is there, 7 quarters is there, and so our one that's in between it is that one. And so it should be this guy right here. But remember how we derived these, or one of the ways that we derived these, was we said, well, add pi to it.
Yeah.
Add pi to that. Ah, yeah, add pi to that. Oh, yeah. It's easy when you're 2 theta. This works out to be kind of nice.
What if it's like not a whole number in there? It's like
Oh, like
2/3 theta.
Oh, you're just gonna be miserable. Your life will be miserable. So let's not do that. Okay, now what's... Oh, I didn't label this. This was 23 pi. 23 pi over 12. Now, okay. What do I do now?
graph
Graph the points. So what's the first point we're graphing?
1 at 0.
1. Okay, now here's the thing. I know that we have 1, -1, and 3. So I'm going to make my 1 about that big. That way I could save room to make 3 about that big. 3 will be the biggest one we have. And so 1 needs to be down here somewhere. So at theta equals 0, we have 1. Then it goes up to what at what output value? Or
Up to 3 at pi over 4.
at pi over 4, it goes up to 3. So that's going to be the long one. I'm going to make him long right there. Okay. Now what happens?
It goes
Pi
back
over
down
2,
to 1 at
back
pi
to
over
1.
Back down to 1 at pi over 2. So there's right there. Nice. Then
0 at 7.
0 at 7 pi over 12, which is that one. So he's going to come in and come in that way. And so I'm just imagining. I'm going to go ahead and prep this part.
And there's
I don't know if you guys ended up doing it this way, but that's how I would probably do it, where I just kind of prep that like that. Now what happens?
it goes down
Negative.
to -1
at
at 3 pi over 4.
At 3 pi over 4,
So that would be in the same- in
he's
the
at
7 pi.
-1, which
Yeah,
is
but it's
now
actually 7.
there.
Yeah.
Yeah.
And now here's the nice thing, is that that same line is what's going to guide you out to there, right? It's that same line
Well,
that's tangent to
this one is
that.
much harder than the ones we have.
Oh yeah, yes it is. That's why I wanted to do one that was wicked hard. So if you could do this one, you got this for review. You have it on video. Like you could refer to this. There's nothing I could throw at you that'll be this bad. So well, of course there is. Okay, so at 7 pi over 4. No. At at 3 pi over 4, we're here. Then he comes back to 0 where?
11 pi over 1.
So he should come back in along with this guy, right? Because there's there's that one. Happens to be the same line.
Yeah, I have no idea.
It's
gonna
going to
be-
be cool. Yeah, you'll see. So, okay. Now we were at 11 pi over 12 and we're at 0. Now, where?
Pi at 1.
Pi gives us a 1, so this should be the same right
Yeah.
there. Okay? Pi gives us a 1, and then it comes out to where at what?
5 pi over 4 and 3.
5 pi over 4 gives us a 3. That's nice. That's really pretty. Okay, now what happens?
3 pi over 2.
Over 2 gives us a 1. Yes, good. A 1 again. So like that. And then what happens?
19 pi over 12. 0.
19 pi over 12, so he curves back in here like this. Okay. And then what happens?
Negative 1 at 7 pi over 4.
7 pi over
Which is
4 gives us a
actually-
negative
So
1.
it's 3 pi.
So here at 3 pi over 4. So he's going to come back out along this one.
What? I keep thinking I know
So
what's
yeah,
gonna
he
look
comes
like.
out like this and then comes out. And then what happens? We're at negative and then he comes
back
back.
to 0 at 23. 23.
And so he's going to come back in like this and be tangent right there.
Oh. And
And then
back to 1.
back to 1. And so he
At
comes
2 pi.
back from there. From here back out.
Oh, at 2 pi, yeah.
Yeah. And so now, okay, this is where this is like you're never gonna get this right. But he's gonna come out, go up to here,
Yeah.
and back down like that. And then we did all this stuff. He comes out, goes over, comes back out here, and then back out. She'll never be able to draw that right. And that's about it.
It's like
Because
a
we did
space.
all the other connections in there and whatnot, and so, bleh.
Is it easier to just draw it when you're finding the point?
Probably, yeah. I mean, especially the more that you get. Like, if there's only 4 points that you're doing, like, whatever, right? But, yeah, it's probably easier to just do it that way.
So what's that called?
Yeah, it looks like if it were in 3 dimensions, this would look like an orbital for like an atom, where an electron goes. There are things like that, and you can see them like in 3 dimensions. They kind of look, and in fact, it is with 3-dimensional polar coordinates that you.
Oh,
imagine
imagine
graphing
graphing
that
that
in
in 3D.
Yeah, exactly. So like you end up with like a donut
Oh.
thing that's like this.
Yeah.
And it's like
Oh, yeah,
that.
yeah.
And then there's these.
Like a spaceship.
Yeah, right. And in 3D polar coordinates, you have that. Only there's with 3 dimensions, you need not just r and theta, you need a theta and a phi. So you have, depending on theta this way and phi this way, you have r going that way, and that's how you end up. But this looks like a cross section of like an orbital, this type of thing. Anyway, so okay, so that's terrible. I'm not going to give you one that bad. It's not going to be that bad. But this would be a great one to practice with. That's why I wanted to do that. And we have 10 minutes. So, okay, that's good. Good. Of course, the other type of thing that we've done is changing from polar to Cartesian and back and forth. Right?
Okay.
So if I give you something, it's like in Cartesian and say find it in polar, not graph it, just find the polar equation.
These are formulas.
Exactly. You should be able to do it just by doing that. So, here's an example. I wanted to do that one. That's going to take too long. So, let's do... here's one from your homework. This isn't so bad. X minus 1 squared. X minus 1 quantity squared plus y squared equals 1. Okay, what are my formulas to change from x's and y's? X is equal to...
R is cosine.
r cosine theta. Y is equal to?
R is sine theta.
R is equal to?
Root x squared plus y squared.
Good. And
Theta. Tan theta.
tan theta. There
Y
you
over
go.
x. Y.
Well, yeah.
Doesn't
Okay.
always.
Yeah, right? Like, it's not always, but if you're using your brain, you could reason it out. Okay, so what am I going to do here? What do I need to write?
You just put in everything in.
And then do it.
So r cosine theta minus 1 squared.
R cos theta. I'm not going to bother with the theta yet. Then what's here?
R sine.
Yeah.
Could probably use the cosine.
And so, what does this work out to be?
R squared cos squared minus 2r.
Nice.
Cos.
2R what?
R cos.
Okay.
Plus 1.
Plus 1. And then
That's just R squared sine squared.
anything we could simplify.
Could factor out an r. R. Oh, you could
Well, let's
factor out
just
the
get the-
sine squared.
Let's get the cos squared and sine squared next section.
That's what I'm thinking. Anytime I see a sine squared and a cos squared, I'm like, well, let's at least do that. But now, we could have taken some other steps that would have been equally as smart. But we'll just do this and notice, oh,
1. Well,
So it's
factor out
just-
R
They
squared.
just go away.
the
But
r
it's
squared.
just
Factor
r.
out the r squared, and you have your cos squared plus sine squared, which goes away. And now 2r cos plus 1 equals 1. Now what do you want to do?
Factor out an r.
Well,
Or get rid of the
we
1.
have a polynomial.
Let's get rid of the, and yeah, okay, so you're, yeah.
Just equal to 0.
Yeah.
Let's get rid of those guys, and that's going to make your life
difference is
much
square.
easier, right?
No.
No. We just said
Yeah.
1 is 1, and so we subtracted 1 from both sides,
Factor
and that
out the
happened to make
R.
your life much easier
And
because
then you just
now
have 2 solutions.
Oh,
So you factor out the r and then you just have
factor out the r, and now you have 2 solutions. Okay, and so either r is equal to 0, which is the most boring function you could possibly have, and you could stop and say, wait a second, is that ever the case that we're at the origin? No, this is you know it's a circle. It doesn't look like it goes through the origin. I don't think it might actually. If the radius is 1 and you shifted over 1,
it would.
it would. And so it makes some sense, but that's not going to tell you what
R
the thing is.
radius.
So we're done. Like, don't worry about that. So therefore,
R equals 2
R equals 2 cos
theta.
theta is your thing. There you go.
Yay.
Okay, and that will go through the origin as that's supposed to. That's cool. Okay, so that should be straightforward. If though we ended up with this, if it were just instead of equal to 1 or whatever, it worked out to be like this,
Then we could factor.
then what would you do? Because that's 1, and so
Then you could just plug it into the quadratic form.
you could.
Oh.
That's what I would do. I would say this is the same thing as 1r squared minus 2 cos. I'm not going to bother with the theta right now. 2 cos times r plus 1 equals 0. And then you'd say, well, x equals negative b plus or minus the square root of b squared minus 4c. And so negative would be 2 cosine plus or minus the square root of, okay, so 2 cosine squared. So 4, how about 4 cosine squared, right?
Yeah.
It's, you got to square that whole thing, so that would be 2 cosine squared theta minus 4 times a times c is just 4. Divided by 2 times a is just that. You could, if you're so inclined, pull out the 4, and you would have 2 cosine plus or minus 2, yeah, thank you, 2 root cosine squared minus 1 over 2. The 2's all cancel, and you get cosine theta plus or minus square root cosine squared minus 1. But cosine squared minus 1 is
Sine.
Square.
No, sine. Wait.
negative.
Oh, negative. Wait.
Negative sine squared.
Oh, but wait.
Oh, so then what? So plus or minus.
Good.
Well, negative sine squared
Negative.
equals sine of negative. You could put the
Oh,
negative
wait,
in
no,
it.
it doesn't. Does that work?
negative sine squared theta equals sine squared of negative theta.
Can you do that with
Sine squared
But
of
that's only
negative.
with cosine.
No.
That's just with cosine.
That's that. Well, here's the thing. So yes, sine does give you the negative of the thing.
Oh, but sine squared.
But sine squared is not the same function.
Yeah.
So you don't know whether or not that's even or odd. It turns out to be even. But
I would bet that you probably will be able to do that.
is sine squared always positive?
Then absolutely.
Yeah, it is. Yeah,
Always
yeah,
positive.
yeah.
So you have a negative of something that's always positive.
But I mean, like,
So it's just negative. You can't take a square root of a negative. Wait, I'm confused.
Oh, we actually have to.
Oh.
That's what it would be if that's what you got. That's not what we got because it wouldn't have been that in the first place. But anyway,
Yeah.
just so you know, like that's how you would deal with that. You'd have a complex answer. And that kind of makes sense because like what this would have been from the very beginning is this. And so like what would you do with that? You'd say, well, if y is equal to 0 or 1, and so you take the square root of both, and like, yeah, it's, well, the thing that you would end up with wouldn't quite be a circle, would it? You know what I'm saying? It's like, yeah, what is that? And so what you're talking about is you have, what this would be is y squared, a squared number is equal to a negative squared number. In other words, you're in the realm of imaginary numbers.
Yeah.
That's what this would be, right? And so, anyway, like, but if you had something like this and you just left it there, or you
Oh,
did
yeah.
some cool
Something
cancellations,
squared plus
that's
something
cool.
squared
If
can't
you don't
equals-
identify that this is an identity, I'm not too concerned about that. Just so you know, in the future, you'll definitely be doing stuff like this. Like, that's, like, you
Something-
want to be able to recognize anytime you have cosine or sine squared minus 1, like, or 1 minus that, then yeah. So I think we're coming up on time. We are coming up on time. Any last questions? You'll definitely have to graph something. And I'm not gonna give you a big flower. That's just evil, right? Like, but
The
do
whole
be
hour.
familiar with cardioids. Do
Yeah.
please be familiar with cardioids. Especially cardioids that do that type of thing. Those are my favorite types of cardioids. Hint, hint.